Good morning. Welcome to this session on climate change, organised by the Environmental Statistics section of the RSS. We've got a great lineup of speakers this morning, and so without further delay, I'd like to invite Jonathan Tawn to come up and start the proceedings. John's going to be talking to us about statistics for heat waves.
Thank you. Okay, so often when we're looking at environmental data, we're often hearing about environmental change, and much of the focus when you hear people talk about that typically focuses on changes in the mean levels. And very little, relatively, is said about what's going to happen in terms of extremes. So I'm going to try to show you various different ways we're trying to redress that in the way we're focusing our analysis. So first of all, why should we worry about extremes and changes in the extremes? Well, if we know about changes in the mean, that doesn't necessarily tell us about how the extremes are going to change. Just a change in the variance will automatically change the tails in a much greater way than a change in the mean can do. And so we've got to be much more aware and develop methods which focus particularly on the extremal aspects of the data to be able to help us identify what's going on in the extremes into the future. Also, changes in the mean maybe aren't that important to us, but in terms of risk, particularly with heat waves and extreme waves, it really is the extreme events that matter. Average values don't really have any impact. Now, looking forward into the future, just using present-day observational data doesn't give us the ability to tease out what's happening in terms of climate change. So essentially, we have to use climate models to tell us what's going on in the future, and there's a range of those, and we've got to try to combine the information from those climate models with observational data to give us as much information about how what changes into the future will affect our extreme events. So in typical applications, we have a mixture of the following. We either have some observational data. Sometimes the people says maybe we shouldn't call this data if it's come out of a numerical model, but we sometimes have data expressed from a numerical model which has been, as well as possible, calibrated to observations as possible. Typically, that's only short and obviously only up to the present day. We also have data from global climate models, and regional versions of those that are driven by the global climate models. So the global climate models contain all the information about different emission scenarios, but they do it at a very coarse scale. And that loses some of the physics of the process, but it also isn't particularly good at, therefore, giving information at particular sites. So regional climate models help bring that information down at a more local scale and capturing some of the physical features at that scale as well. And then with the climate models, we don't really know what's going to happen in the future, so we've got to consider about different scenarios, and therefore we want to understand how different scenarios affect the extremes in different ways. And also there's the fact that there is no exact climate model. So climate models have been run over different variants of them, incorporating different, I suppose you could say, uncertainty in their parameters to try to see the sensitivity of those uncertainties on the extremal features. So once you've run one of these climate models, you could just look at the extremes of the data from that to try to interpret what's going on. But the complication with that is that you'd have to run the model for a very long period of time at a huge computational cost to be able to extract all the extremal features you need. So we need a way of reducing that uncertainty by actually incorporating some extra information from within the range of the data to help us extrapolate to larger extreme events. There's also a problem that numerical models aren't quite capturing exactly what's going on in practice, and particularly because they're looking at things at different scales, and so therefore there's some biases that need accounting for. So they're the types of features we have to address in the statistical modeling. So there's some element needed for recalibration of the information we see from the numerical models. You could think of that as the downscaling information. And obviously, what we're going to try to do is exploit the fact that we can't get into the tails with the model data alone. So we're going to have to supplement that with some extreme value top theory to help us extrapolate from the information we see in the observed tail of the modeled data out to rarer events. So we've got this complication that we can do various things here, but what we're looking at is processes on different spatial aggregation scales. So there's a global climate model at one big scale, regional climate model at a reduced scale, and then observational data effectively at a point location. And so therefore, naturally, when you look at a process at these different aggregation scales, you'll see different features, and what you'd really like to be able to do is move between these different scales in a way that you had confidence at how the different properties interrelate with each other. The other aspect, as we'll see in one of the examples I'm going to look at, is that the global climate model doesn't actually contain the variable you want to study. And so therefore you need to connect it somehow to the variables you are interested in studying. So as I say, from the title, we're going to look at these in terms of heat waves as an example, and also in terms of sea waves, where we'll look at the wave variability, which is a significant wave height, but I'll just call it wave height to make it easier. Okay, so just some extreme value building blocks that we're going to use inside the analysis. So the basic extreme value approach is to focus on the maximum of a set of stationary random variables x1 to xn. So you pick out the maximum of those, and we model those using an asymptotically justified model based on limit theory as n tends to infinity, that the maximum can effectively be described by only one class of distribution, the generalized extreme value distribution. That's a three-parameter distribution, a location, scale, and shape parameter mu, sigma, and psi. And the critical thing for us today is that the support of that distribution depends on those parameters, because essentially the thing in the square box there has to be positive. So therefore, we don't know in advance what the support of this distribution is, and part of our inference determines that. So I'm going to use this notation for the GV just to, in terms of its parameters, just for ease later on. Now, another building block in extremes is rather than just studying the distribution of the maximum, study the tail of an individual random variable x. And the same type of asymptotic theory tells us as we let a threshold level tend to infinity, or tend to the upper end point of distribution, it tells us what the excess distribution should look like in such a case. And similar limit theory to before, as I say, gives us that this distribution can only be in one class of distributions. It's in this family of distributions called generalized Pareto distribution. And in practice, what you then do is you pick a high threshold, you model the number of exceedances above the high threshold as following a Poisson distribution, and then you model the excesses of the threshold using this generalized Pareto distribution here. Now, I like to think of it really, rather than as a conditional distribution, I like to think of it as an unconditional tail model. So it's telling us about the tail of a random variable x above some level y, which is bigger than the threshold. And it then comes down to a three-parameter model. So it's very much like the GV, but instead of the GV, which applies to maxima, this will apply to the tails of the original variables. Now, if we've got a non-stationary world, we obviously have to move away from the basic GV with the parameters fixed, but a natural starting point might be to think of, say, that if things are changing very little in a year, but over years are changing quite a lot, to think about modeling the maximum in year t as a GV, but with the parameters potentially changing as a function of time. And in typical applications in environment, we see that the shape parameter doesn't change very much through time, but so we can often take that constant, but the location and the scale parameter tend to, so we tend to model those as some form of linear function of the covariates. Time's a poor covariate, because it's not causal to the cause, the climate change isn't changing because of time. So we need to put some of the physical covariates in there. So in the studies I'm going to show you today, I'm putting in the global mean annual global mean temperature as a covariate GT. And if what I'm presenting here, we can extend and do the same type of ideas for a GPD situation. So look at heat waves first of all. Heat waves are sort of interesting because they're not so well defined. But what clearly determines a heat wave is that what the marginal distribution of a process is like, so how its distribution is, and therefore how its distribution changes over time. Something to do also with the temporal dependence structure, because a heat wave is something not just about instantaneous temperature, but about prolonged temperature being extreme. So we have to model the dependence structure between consecutive observations in some way. And then we did this by using Markov models. And because we're only interested in the extreme states, we don't use a model just to describe one transition to another, but we only model that during an extreme stage of a process. So we have to use particular types of copulas to be able to do that. And obviously, a heat wave involves some spatial dimension as well, which I'm ignoring today. But heat waves, as I say, can be defined in different ways. So what you really want is you'd like a model for a process above a high threshold level, and therefore from that model you can extract all the different heat wave definition characteristics you might want. So if we just think about the heat wave, it's not as simple as just that peak weight value or the duration. It's something to do with sort of integrating the effect together of the whole profile above the threshold. So the reason I got first interested in this was we were looking at the 2003 European heat wave, which caused 40,000 deaths in France. This was a temperature of 39.9 centigrade, so the peak temperature was that. But the critical thing that made it so bad was that for 11 consecutive days, the heat stayed above the 1-year return level, which is about 31 or 32 degrees from memory. So it stayed in this extreme state for a particularly long time. So what we'd like to do is understand how events like this change and become more common in the future as under climate change. So the data we have to study this was we had 13 different global climate models with different effective parameters running these, so they're all run independently of each other. But we looked at one, first of all, let's think about, we look at one climate change scenario, and I'll give you the results of that. This is a very strong climate change signal. And as I say, we used the global temperature as a covariate, and we found it's only really, at a superficial level, if you simplify the calculations down, it's only really affecting the location parameter of the tail of the variable. Critically, we find that there's no change in any of the 13 GCMs in terms of a dependence structure over time. So the good thing with that is that we aren't getting stronger dependence over time, so the events aren't, in theory, lasting longer. But longer's a hard thing to measure, because longer's relative to what the marginal distribution is. So you could think there's no, in terms of, relative to 1-year level, whatever that is at every stage in time, they aren't getting longer in terms of their duration above that. But the 1-year level's increasing over time. So relative to today's 1-year level, we'll get much longer events in the future that exceed that, even though the dependence structure isn't changing. So the types of things we find in this analysis are, if we just focus on the peak level, and maybe just jump down to this one first of all, is that what we're finding, if we just focus on one of the GCM runs, just to illustrate it, we get a change. If there's a 1 degree temperature change in the mean global temperature, the extremes are going up by nearly 2 degrees for an event as rare as the 2003 event, and with a reasonably wide, decent confidence interval around that. But that's obviously just for one of the GCMs. I mean, if you run the 13 GCMs and look at the sort of range of uncertainties, combining all the confidence intervals together, we see that there's a wider range of uncertainties how the extreme temperature will increase in this place relative to a 1 degree temperature. So the extremes are going up faster than the mean. And in particular, if you go much further forward to a 5 degree temperature rise in the global mean, we're getting a much, much larger change in this extreme level, which is rather worrying. Now, we find that we get the same relative changes for all the different other scenarios that we ran. What happens is the key differences between these is that the time until you get a 1 degree change is different from one model to another. Sometimes it can happen very quickly if we put extreme emission scenarios. In other cases, it takes a much longer till we get that. But if we just look relative to the global mean temperature, we get this quite consistent results across different scenarios. Okay, so the second study I'm going to look at is focusing on extreme waves. And this is work with Shell, and what we've been trying to do there is look at design of offshore oil rigs into the future, and in particular thinking about what would happen in terms of design if we had to design something now, but wanted it to last up to 2050. And we'd like to estimate these return levels, these high return levels, somewhere between 50 and 1,000-year return levels for in that future time period. What we're going to do is focus on this area of the northern North Sea, which is sheltered by the Shetlands, and so directional waves is an important aspect there because of, we get different wave characteristics from different directions, partly due to the sheltering and partly due to the weather systems that come across. Now, the data we have here, we have GCM. In this case, I'm just running it from one model just to illustrate the approach, but we also have numerical model data which has been driven by the weather systems now, but this is numerical model on both winds and waves over this area in the northern North Sea, and this gives us this data at a fine scale. Now, the numerical model data of the wave model has information on all the key variables I'm interested in terms of wave heights and wave directions. It also has it on the wind speeds and directions, whereas the global climate model only has the information coming out of it about the waves. So we need to adjust and understand how, therefore, changes in wind speed linked to then changes in wave height to be able to get a connection into what's happening to the wave heights into the future. So just to see some structure between these various different features, here's a plot at one of the sites we're looking at the wind speed against the wave height, and you can see that this is with the model data in the present day conditions, and we can see there's a very clear relationship. And you can see also there's an awful lot of structure in here if you look at direction against wave heights, that we can see the land shadow of the Shetlands here, reducing wave heights from that direction. So the strategy we're going to do is look at the mauve boxes over here and build a topographical model of the relationships between the different variables. So the wave direction, so the wind direction influences the wind speed. It also introduces the wave direction, as does the wave height, and then they all feed into describing the wave height. So we've tried to build this model on the observed data, but then we can use information about how these wave variables, in terms of direction and the speed, wind variables, how they change over time from the global climate model. And what we're trying to do is then find given how that changes, the wave direction changes, we can find a link to see what would be the implications there. And again, we look at the conditional distribution of the winds given the waves, given directions, and we can adjust for that as well. So the basic setup, ignore the top two lines. We've got We've got the wind variable from the global climate model, both in the present period and in the future. And then from the wave model, we've got also the winds from that, and we've got those at the present time and in the future. And what we'd like to do is be able to translate by seeing that the present day winds from the global climate model, and then in the future, they're changing in a particular way, and we'd like to see how that implies that the waves from the local model would also change. So we're trying to estimate this new distribution in some way. So to be able to do this, we need to be able to interlink somehow how these distributions are connected. And the classic way to do this is through this particular formula that's been around for a long time, but it's got problems, which I don't think have been identified before. So if you first of all look at this step in here, this inverse puts these things back on the units of xp, and this requires the units of yp. Now, in my case, they are the same variable, but they don't have to be for this downscaling step. So therefore, if they're not on the same units, this doesn't work. They also must have to have the same support, and as I said, we don't necessarily have that within the data that we're looking at. So if we instead think about a different way to derive this relationship, what we can think about instead is thinking about how the climate model can connect somehow to the wave model in terms of winds at the present time, and think there's a transformation that makes those equal in distribution, and then think, well, in the future, that relationship, because it's a physical relationship, should hold into the future in the same way, even under climate change, so that these two distributions are connected. So we've got this function t is really a mapping from one quantile scale to another to tell us how these two variables are connected. We believe that that's physical and going into the future. Now, if you track that through, you now find a new result that connects the distribution functions in a particular way. But it sorted that problem out from before, because this is the same variable, we've got the same units and it all works there. So our proposal is to use this type of approach to derive the new distribution function, but by first estimating each of the distributions we have data on, and particularly focusing on their tails using the GPD. So just to quickly show how that works, what we can see here is some data from 2 different directional sectors, and we're looking at the quantiles of the wind speed against the quantiles of the wave heights. And you can see that it's actually a very, very simple relationship, even though these things aren't that, if you put them at the same time, they're not easy to connect. But if you just look at their quantiles, you can see that they're very nicely connected in this situation. And we can model that, and we can model it in this particular case with just a very straightforward linear model, and we can model how it changes with directional sector as well. So that gives us, in the end, a model for how to translate and derive a new distribution from the information of the other distributions. So we can move forward into time this relationship. And when you do that and combine that through with this graphical model for the other parts of the relationship, you can derive out from that all the future type characteristics of the extremes into the future. So in particular, if you look at the sort of 50-year level now, it's 15 meters, 15.1, it's sort of in theory in the future is going to increase. The uncertainties on both of these are quite wide because we haven't tried to narrow down apart from the 10-year period of information, but clearly we can pull across neighbouring years very easily to reduce these if we wanted. So it looks like, again, that the extremes are increasing. We've used this method to be able to tailor things through here. The uncertainties represent Monte Carlo uncertainties. They represent inference uncertainties through our different modelling steps we've had to do here. And although I haven't shown it, these results also apply over space and also account for you can get directional results as well. So therefore, in particular, we can see that in certain directions, there's a greater level of change than in other directions over time due to the climate change. So I've just got 2 minutes left. Yeah, so just to finish on some work we're doing at the moment, trying to understand the relationship between variables on different spatial scales, which obviously ties in with the point data to global or regional climate model data. So consider a situation where we've got YS as a spatial process. We may be only observing it at D sites, and we want to add up to see what that process looks like and its distributional properties as we look at the sum of those. Obviously, we know if we sum something enough and we don't look at the extremes particularly, we know we'd get a normal distribution from the central limit theorem. But what happens if we focus in at the tails as we sum? So what we've been looking at is looking where the Y process has a common marginal distribution across space. So it's got a common scale and a common shape parameter, and it can have any top dependent structure at all. And we've been able to derive that the distribution of a sum of these variables, in particular if the common shape parameter is positive, the sum of these variables also has to have exactly the same shape parameter. And we've been able to find how the scale parameter connects to the various features. It depends on the dependent structure in the copula, the dimension, and the original scale parameter. So relatively straightforward. In the case where it's got an upper end point, so a negative shape parameter, we see that the shape parameter of a sum here becomes much more subtle. It's not the original shape parameter, but it's now controlled by this parameter eta, which is something to do with the extremal dependence in the tail of the multivector variable. And in particular, eta lies between 1 and 1 over d for positively dependent processes, and you can see particular examples of it here for different classes. So we can actually see that in particular, so with a negative tail, that's a short tail, but as the shape parameter gets nearer and nearer 0, it gets more like an exponential tail. So the effect of summing here is to effectively lengthen the tail of the variables relative to their individual values if we have some element of weaker dependence between the variables there. So just a final slide from me is just to show what we're trying to do at the moment is look to see how much we can learn and lose at different scales of this aggregation process. So our first test of this has been to look at some rainfall data and aggregate the data from the numerical model from the regional model up to a grid scale of the global climate model. And over the UK, there's 5 grid boxes corresponding to the global climate model. And so if we do that, we should obviously, if they were measuring exactly the same thing, we'd get exactly the same results, but they've been running connected, but not to ensure they're exactly the same. So in each of the regions, you can see that this is the trend parameter over data from a long period going into the future. We can see that the 2 models, relative to the uncertainties of the parameters, are capturing trends in a very similar way to one another. The feature I pointed out that the shape parameter shouldn't change as we aggregate up. For a positive shape parameter, would suggest at least we should get things that are very close. We're getting slight changes in these, and the shape parameter is coming out as negative, suggesting that there's some effect of a dependence there. And we can see that in terms of return levels, we've got a very similar connection between the results. So what I want to do, and just as a conclusion, is to try to extend this work, bringing this theory in to enable us to look at extremes of data looked at all sorts of different spatial aggregation scales, and so we can move between those with confidence. Okay, I'll stop there. Thank you.
Thank you very much. That was a great talk. I have a clarification question for this slide. So the RCMs, are they run with different GCMs as boundary conditions or the same GCM?
Same GCM in this case, yeah. But of course, that doesn't necessarily mean that aggregated over that grid box, it's going to give the same values, which is why we get this difference. But yes, they've been run on the same boundary conditions, yeah.
Perfect, thank you.
Okay.
Thanks very much, very interesting talk. Just a question which is very general and perhaps out of the scope of the talk, but I'll do it anyway. Do you see any advantage of not only looking at exceedances or the tail of the distribution, but actually looking at the first, at the maxima, the record process, let's say? Would there be any advantage or anything to gain by modeling the process of actual records of waves or temperature or things like that? Or do you think that's not... that doesn't add anything to what you gain by these models?
I'm struggling to quite hear what you're saying, sorry.
Sorry. What I'm talking about is, the question is this, do you think there's any advantage on looking at the record process as opposed to exceedances or extreme values? Yeah.
So, I mean, one of the things we know within, so the questions about whether you should look at records v non-records. Records are interesting events, obviously, but the complication, if you had a stationary process, if you've got n observations, the number of records you only get is log n. So the amount of data you're throwing away effectively if you just focus on records is very weak. I mean, what you can do, I think, is the better approach is to really focus on looking at modelling the whole process and then study the properties of records in relation to that to see if they're consistent with the model overall. Yeah, sorry, I didn't get the question first time.
Thanks, a really nice talk. Yeah, I was interested in the function T, which is obviously really important for linking your climate model with the wave model and allowing the information to flow from the two sources. Getting that function right is going to be critical for your extrapolation. How confident are you that it's working?
Yeah, that's a good question. I mean, there's no mathematical theory that tells you in advance how the type of form that T can take, unlike the rest of the extreme values where you get a structure given to you by limit theory. What you're usually trying to do here, though, is downscale between variables which you know are somewhat connected, and so therefore you would believe there's some relatively simple physical relationship with them at the point scale you're looking at. But it might be that you need to do this more effectively by not just looking at the global climate model on the nearest region, but sort of recognizing there's some spatial connections between these things at different scales again. So you maybe have to not just use the nearest grid box, but maybe some weighted combination of different other grid boxes to try to improve that relationship. So you're trying to pick as much physical structure as you can, but certainly in the applications we had, it was easy, but I'm not quite so sure how easy it would be in other contexts. The beauty is, because you're only comparing quantile to quantile as opposed to observation to observation, it massively cleans up the relationship you're looking for.
Right. Thank you, John.
Okay.
Our second speaker today is Andrew Parnell, who's joined us from Maynooth University in Ireland. Andrew's going to be talking to us about Bayesian Additive Regression Trees for palaeoclimate reconstruction.
Great, thank you very much. Pleasure to be here. I get to talk to you for 25 minutes about two of my favourite topics, which are Bayesian additive regression trees and past climate reconstruction. So, see if this works. There we go. So what I'd like for you to get out of this talk over the next 25 minutes, I'm going to teach you how this whole thing works, how paleoclimate reconstruction can be seen in quite a general kind of statistical framework. Then I'm going to tell you about what Bayesian additive regression trees are, because not everybody knows what they are. And then you might think about how you might become involved in this research. And we always need help. We always need more people working on this. Not enough statisticians get involved with this. And it would really help to have more people doing it. So why should we care about this? Let's start with a plot. This is a plot of an ice core. It's an ice core from Greenland, and it goes back 100,000 years. So you can see on the left-hand bit of the plot is 100,000 years ago, and it goes up in 10,000-year chunks until it hits the present. And if you look closely at the squiggly line and how it moves up and down and changes, you see that the last 10,000 years, almost all of human history is encompassed in that, and it's completely different to the previous 90,000 years. So it's really interesting to look at how fast climate can change, and the size of those changes, and whether this is relevant not just to Greenland, but whether this happened in other places in the world as well. And this is data. This isn't output from models or anything like that. This is numbers which are coming out of a scientific experiment. But of course, there's one thing I haven't explained to you on there at all, is it? Can you see what it is? I haven't told you at all what the vertical axis is actually on that plot. Okay, it's delta 18O, which is some bizarre measurement of the oxygen content in the bubbles in the ice. It's supposed to represent the warmth of the rainfall that's falling on Greenland. Okay, it's not temperature, it's not rainfall, it's some kind of bizarre measurement that's commonly known as a proxy. It's a proxy for climate, but it's not climate itself. The thing we need to do to extract the useful information out of that data series is turn that delta 18O into something that's useful to us, be it temperature, be it rainfall, precipitation, so on. So that's the kind of thing we want to do, and why this is all important. It isn't just ice you can do it with, though ice is one of the most popular ones. Obviously, you can only really get ice from the two poles. You can get it from mountain ranges, though it tends to be a little bit noisier there. A common one that people get it from are tree rings. So you can use things like the width of the ring will tell you how warm the summer was or not. You can use insects as well. There's a specific type of insects called non-biting midges or chironomids, which are extremely sensitive to changes in climate. And people use those very often for reconstructing past climate. But the one I'm going to talk most about today is pollen. Okay, there's a couple of grains on the bottom right there of alder pollen. People dig these out of lakes. They take huge sediment cores out of the bottoms of a lake from anywhere in the world, and those lakes have acted like little dustbins. They've sat there for thousands of years, like those ice sheets, and have just collected the pollen rain that's collected on the surface of the lake and has sunk down and has created this core. When you get it out of the lake, you slice it up, and there's experts who can count and identify the different types of pollen. It never looks like that on the screen. It's crushed, it's broken, it requires real expertise to actually do this. People have talked for years about finding some automated machine learning way of identifying pollen, but nobody's come up with one yet. Maybe you'd like to try. Let me show you how the data actually looks like when you actually do these paleoclimate reconstructions. So you have your core that you take out of the lake, you slice it up, and you count the pollen in it. But to turn that into climate, you need a calibration data set. So the thing people also often do is they go around the world and they take surface samples of soil as well. And in those surface samples, they can also count the pollen and the types of pollen, but they know the climate because it's the present day. So you end up with these two different data sets, what I'm going to call the calibration data set and the fossil data set. And this is roughly what they look like. Okay, so you've got your calibration data set at the top. It's all from the present in my examples. You've got your climate variables that you're interested in. You can choose things like mean annual temperature here if you want to, but that is dangerous because, of course, plants do not respond to mean annual temperature. They respond to things like extremes, to things to do with the length of the summer and the harshness of the winter and so forth. And then you have all of these proxy data. So this will be different counts of different types of pollen, but it doesn't have to be just pollen. It can be other things as well. It can be things like chironomids or tree ring data and things like that. So you've got this modern data set, looks a little bit like this. You've got your climate variable, you've got your proxy data set, and you've usually got several thousand of those in your modern data set. And then you've got your fossil data set. So this one goes back in time. You've actually got year here. I've put it as kind of like an integer thing, but as we'll see in a second, it's usually a continuous time series down there. You've then got the proxy data from the fossil thing that you've taken out of the bottom of a lake. The thing you're missing is the stuff in red. You don't have past climate. Okay? That's the thing you're really interested in. So your job as statisticians is to take that calibration data set, take the ages and the proxy data, and fill in those red missing values with uncertainty. That's how the whole thing of paleoclimate reconstruction works. This is what the calibration data set looks like. I thought I'd show you some real numbers just to make it a little bit more concrete. I don't know whether you're used to looking at tibbles from R, but I'm getting slowly used to them now. So in this modern calibration data set, we have 7,742 surface samples. It has 31 columns. The first 3 columns you can see there are climate variables. GDD5 is like the length of the summer, MTCO is the harshness of the winter, and AET is some kind of measure of moisture available. And then the others that you can see there are all the Latin names for all of these different pollen taxa, which I always forget, okay? So we've got things like alder and oak and all kinds of other things in there. This is all just presence, absence data. All of those pollen data there are binary. It was either there or it was not there. If it's there, you know it likes that particular climate. If it's not there, you don't know whether it's because it doesn't like that particular climate or because they just didn't find it. Okay? So that's the calibration data. And the data set I'm going to be using for my fossil data has 924 layers. You can see the first column there is age. So we're going back in time because obviously as you go down the slices in the core, it has to get older. If that doesn't happen, you're completely in trouble and the whole thing will break. So 0.059 there means 59 years before present. So everything's in thousands of years. And present in the world of climatology is often 1950 AD. So what they usually mean by that is 59 years before 1950 AD. And again, in the fossil data, presence or absence. Was that type of pollen found in the data or not? So you might be thinking already about how you might solve that particular problem. You've got that red column to fill in. But of course, as you've seen now, that red column is multivariate. It's not one climate variable. In my data set, it's 3. In other data sets, you might have 5 or 10 or even 20 different climate variables, all of which you don't have for the fossil core and you want to fill in. The common thing that people do, because it looks like a regression problem, is they treat climate as the response variable, they treat pollen, presence or absence, as the explanatory variable, they fit a regression model on the calibration data set, and they use that to predict the red bits, the missing climate variables. Seems like the obvious things to do. It's such a traditional standard regression problem, it surely must work. But it really doesn't work well at all. And in fact, you're much better off doing it the other way around, treating the proxy data, the pollen, as the response variable and treating the climate as the explanatory variables. That makes so much more sense when you think about it because, of course, the climate changes are causing the changes in the pollen concentration, not the other way around. If you're going to include things like mechanistic models or anything like that, if you're going to deal with measurement error, it's far, far, far easier to treat the proxy data as the response rather than the other way around. But unfortunately, that other way around is the traditional way of doing it. If you treat everything as kind of Gaussian, then it kind of works, but not very well with binary data. So let me show you a little bit of maths about how this Bayesian version works. We do it in a Bayesian fashion, and I think almost anybody who came at this and realized that you have to do it by putting proxy as the response variable would do it in this way, because of course Bayesian inference does beautiful inversion of that relationship. You can build a model for the proxy given the climate, but what you want in inference is the other way around. You want climate given the proxy information. So if you want a posterior distribution of climate given the proxy information and the calibration information where you've got both, you're going to write that as proportional to the proxy information given the climate information times some prior distribution on climate. And this is where your imagination can really start to run away with you, because once you've got it in that framework, you can pick what kind of models suit your particular data. So if you've got spatial data, that prior on C over on the right-hand side can be some kind of spatial model, or it can be some continuous time series model, and you can use all kinds of fancy models for that likelihood term, where you're modeling the proxy given the climate. And that's the bit I'm going to focus on and do the fancy BART stuff with. If you want to start adding in parameters into that, it gets a little bit more complicated, but it's the same thing. You've got a calibration model, which has parameters theta, pcal given ccal theta, and you apply that again to the fossil data, p given c theta. You've got some parameters phi, which model how climate changes over time or space or both, and you've got some priors on those parameters as well. But the whole thing just comes out, you just turn the standard Bayesian handle once you've got those likelihoods and priors set up, and you get what you want. It's posterior distribution of climate and the nuisance parameters given all of that data you've got. fossil proxy data and calibration proxy data and calibration climate data. So once you set that up, it all works out swimmingly. We have an R package which does this called bclim, which does it particularly for pollen and makes certain choices for this. It can be exceedingly slow to build some of these models because of the complex interactions that are going on. In particular, it's really tempting to build individual models for each pollen or each proxy in turn, do things like logistic regression or something on each one, but there's complex dependencies going on here. These functions are non-linear. They interact in the climate variables. They are not conditionally independent between proxies. You need some kind of multivariate model to actually get this to work. Here's an example of the kind of thing you can produce. This is a lake which has sat in Italy, south central Italy, for about 120,000 years. And if you set up the model, which I'm going to explain how it works, you run it through. We use a continuous time series model, which is based on a normal inverse Gaussian distribution, which enables us to model climate changing smoothly and rapidly as it goes through. You get this kind of thing. So the red bands you can see there are the posterior distributions of this is moisture over time, moisture available to plants over time, going back 130,000 years. So this is going back even further than that ice core that we saw. And then obviously when you run a Bayesian model, you've got individual climate histories, which some of our climatologist friends find really, really useful to look at. So those are the individual blue lines in there. And again, you can see that the last 10,000 years has been more or less stable, and then you start to see big changes. Interestingly as well, if you look at about 30,000 years before present, you'll see that there's a big jump in uncertainty there. That's because there's no pollen for any of that particular bit of the fossil pollen course. The uncertainty balloons out and then balloons back again. I've plotted one climate variable here. I could have plotted any of the other two as well, which is the harshness of the winter and the length of the season. So you plug these bits into your model, you turn the Bayesian handle, and you get this kind of thing out the other end, and that enables people to start to compare past climate change, how fast climate can change in one location to different locations as they go through. Both wonderfully and terribly, it's really hard to check these models, because of course the only bit you can check is the modern calibration model. The only bit where you can actually do things like leave one out cross-validation. There's no obvious way to check the past climate reconstructions. There's nothing there to compare them to other than other people's past climate reconstructions, and you might completely disagree with the models that they used to actually create them. So it's a terrible thing, but on the other hand, it's wonderful because you can't be proved wrong. You're always right. A lot of people do fake data simulation. They call it pseudo-proxy experiments. But again, these often depend on a model, and surprise, surprise, if you simulate from a particular model, that model tends to win when you compare between them. So it's a really interestingly challenging field to check that these things are actually coming out correctly. So this stuff is hard, okay? So the calibration models the calibration data sets tend to be quite big. You've got a multivariate Bernoulli response variable here, which is fiddly to do with. You've got complex nonlinear interactions between the explanatory variables, the climate variables here as well. So we spent a long time looking at Markov random field models, looking at INLA, and every time we tried to expand it out to larger data sets and higher dimensional data sets, they'd just fail or they'd be too slow, and it really didn't work for us. So we tried for a while using various machine learning approaches like random forests and so on, but of course they kind of throw out all the uncertainty and they don't really fit the model structure that you want at hand. And I've been a big fan of using Bayesian additive regression trees for a while now in other areas, in bioinformatics, and I just thought it would be good to see how they kind of worked in this particular situation, because they've got all the richness of the complexity that machine learning models can handle, but also allow for uncertainty and things like that, which is what we want for our paleoclimate reconstructions. So let me give you a quick introduction to BART. It's kind of similar to random forests or gradient-boosted trees, if you've come across those. It's a sum of trees model. And I'll show you a tree in a second. But if you give me an explanatory variable, I run it down my particular trees in turn, and at each leaf of the tree, I get a prediction. Okay? And then I do that for all of my trees in my little forest, and I add up those predictions, and that produces my overall response variable. So you've got TJ is a tree, and I'll show you one of those in a second. A tree is structured so it has splits, it has if-else statements as it's going down it, and you want to learn what those variables it should split on, and at the bottom of the tree it has terminal nodes, and they're your predictions that you take from each tree and add up. If you're clever, or if other people have been clever and have chosen prior distributions well for these terminal nodes, you can get wonderful computational speed-ups. It fits beautifully. It produces wonderful predictions. It really is a brilliant model. If you're doing kind of machine learning type things and you want to get back towards statistics, I thoroughly recommend trying BART. It's brilliant. And there's a couple of really good packages such as BART Machine, which will do the job for you. But we didn't want to use those directly. We wanted to build our own version. So anyway, here's an example of a tree. So this tree splits first on variable x3. If it's less than 0.47, you follow one particular route. If it's greater than or equal to 0.47, you follow another route. As you go down the tree, you hit the terminal nodes. And so if your particular x combination leads you to that top value there, your prediction will be minus 0.47. Usually you build these models with 10, 20, 30, 40, 100 trees, and you add up those predictions from each terminal node of the tree for your specific x values. And that's what gives you the predictions. It does a beautiful job of nonlinearity. It does a wonderful job of interacting variables and complexity. It really is a fun thing to do. And as you run it, it learns those trees. It grows the trees. It learns about what the split variables are, what values it should split on, and what those terminal node predictions should be as it goes through. So we wanted to use this for BART, but we haven't got just a straightforward univariate continuous response variable. We've got a multivariate binary response variable. So we needed to build multivariate Bernoulli BART, which is what we've been doing. So that first term, that key bit of the likelihood here, which is our proxy given our climates. So we've got 28-dimensional proxies. We've got a 28-dimensional multivariate Bernoulli distribution for this. We've got 3 explanatory variables because we've got 3 climate variables. And this is now going to be a multivariate Bernoulli BART. And then again, once you've got that set up, you just turn the Bayesian handle, you combine it with our time series prior for how climate changes, and the whole thing runs very, very nicely. You might be familiar with how you can set up Bernoulli regression using continuous variables. There's a famous kind of Albert and Chib approach, whereby if your response variable is 1, you say a latent variable zi is greater than 0, and if that's less than 0, then you set pi to be 0. And that enables you to run just a standard regression on that latent variable in the background, and there's a couple of clever little updates which enable it to satisfy the probit regression approach. You can also do that a multivariate way. So if you've now got our 28-dimensional thing here, we're now going to have a 28-dimensional multivariate latent response variable, and we're going to model that as a multivariate BART. And my postdoc assures me that if you prove this way, you end up with a valid multivariate Bernoulli distribution if you do this. So we've got multivariate Bernoulli BART running in the background. As I said, the only bit of this you can check is the calibration model. So we can run, for example, if you saw we had about 7,700 modern data points. If you run it on those and then look at things like AUC values, you get pretty good performance. This is BART with 20 trees. As I noticed on the train on the way up here, this is actually in-sample prediction. So I reran it on the train, fitting it to 7,000 of the observations and leaving out about 700 and looking at how it did. And unfortunately, that didn't make the final slides. But these go down by quite a bit, so by about 0.2 in each case. They get quite a bit worse when you look at out-of-bag prediction performance. But you've got to remember, we've got 28 of these variables, and every single pollen taxa is providing a little bit of extra strength as you go through. So they are all contributing their own little bit towards us learning about harshness of the winter, the growing degree days, and the amount of moisture available. So when you end up at that particular point, this is the kind of thing you do. So you've got your multivariate Bernoulli BART, which is running on this calibration data. It's taking all these 1s and 0s. In the background is this latent set of latent variables, and a full BART is running on that. That's being combined with a climate time series in this approach, which uses the normal inverse Gaussian distribution to enable smooth and jumping things everywhere. There's a load of fitting tricks in the background, which I'm not going to talk about, but they're in some of our papers to actually get this to run fast. Most of this is in our package, bclim, and so you can use that to do this kind of thing. So you turn the Bayesian handle, and what that outputs at the end are posterior histories of climate. Okay, so you've got those blue lines there. That's just three of them, three of the representative climate histories. But when you summarize thousands or tens of thousands of them, you get those kind of red uncertainty bars, which are the 50, the 75%, and the 95% posterior uncertainty bands. And people can now do this. They can do this for any of the pollen sites across Europe. We don't have to do this for just pollen. There are lots of other different types of proxies. So for example, we do this quite often for sea level as well. There are different proxies that people use for measuring sea level changes over thousands of years. And we can use exactly the same approach. The maths in the background stays exactly the same as you go through. And this means that people can finally compare these different sites with properly quantified uncertainties rather than just producing single lines and things like that, which is what they were traditionally doing. Or doing it the wrong way around and treating climate as the response variable in the model. So there's various things I haven't talked about. We don't actually just have the binary yes or no information. We also have counts for both the calibration set of the number of pollen grains in each slice. But we haven't yet built a multinomial version of BART. It can be done, but the problem when you start to use the counts is there's a huge problem of zero inflation. Okay, so you have huge swathes of the calibration data set where they just don't find anything. And building those kind of zero inflation models for multinomial data is really fiddly. If you think about it from a binomial perspective, if you zero inflate one thing, everything else gets n-inflated. So you end up with n-inflation and zero inflation. It's called endpoint inflation. In the multinomial case, you can imagine how complicated that gets. One pollen taxa gets sent to zero, the others all get sent up, some get sent to n, some get sent lower. It becomes a huge mess, and we haven't worked out how to do multivariate endpoint inflated multinomial BART yet. We haven't started to include more than 2 or 3 sites together. We can do 2 or 3 sites simultaneously with a simple spatial model, but it just gets way too slow and complicated when you start to build it up and try and do, say, the whole of Europe and do a paleoclimate reconstruction for the whole of Europe. Still can't do that yet, too computationally challenging for the kind of models that we want to use. And in the background as well it's not just climate that's changing pollen. There are other things going on as well. It could be to do with the local site in particular. It could be to do with the aspect of the lake. It could be something else that happens. Sometimes you see in some of these cores, as you get to the present, it gets colder. That's not because it actually got colder. It's because humans arrived and chopped down all the trees. So you want to be careful about the present, and you might want to include things like mechanistic models, which do exist for how pollen disperses in response to not just climate change, but other things that are going on there. So, as I said, I use BART not just for paleoclimate research, but also quite often in genomics and genetics. And I'd just like to point out to anyone in the room that I do have a new EU project and a 3-year postdoc, which is to do with developing BART for high-dimensional SNP genomic data, in particular for breeding wheat. So we're using these kind of methods and these kind of models for breeding wheat. So if you have good PhD students who are looking for postdocs and might want to come and work here, I'd be really delighted to speak to you. Thank you very much. Cheers.
Okay, our final speaker this morning is Thordis Thorarinsdottir, who's kindly joined us all the way from the Norwegian Computing Centre.
Good afternoon, everyone. And I want to thank Phil very much for organizing the session and inviting me to speak here. So, I'm going to talk about decision support for climate change adaptation, especially the importance of looking at the uncertainties in the system. And it's actually nice that my talk is after Jonathan's talk, because it's sort of an addendum to his talk. It's basically what happens after we do the work that Jonathan's been doing in some sense. And this is collaboration with my colleague, Peter Guttorp, and then Karianne de Bruyn, who's an environmental economist, Martin Drews, and Peter Schell, who are climate scientists. So, there we go. So this is sort of what we often do when we think about climate change modeling. We start with some assumptions about scenarios for the future, emission scenarios, and then a lot of things happen. And what we end up with is a report that tells us something about the expected climate change in a specific region. So this is a report that came out January 2017 about Oslo municipality and Akershus, which is the municipality around Oslo. So if we go in and we read in this report, we will see that it rains a lot already in Oslo, and it's going to rain even more. And for instance, just down the hill from my house, at my bus stop, we have this pop-up lake. Every time we have heavy precipitation, and we're going to see this lake more often in the future. So that's sort of all good. But then if we want to actually do some climate change adaptation, that's actually not enough, because we can only have an adaptation measure being implemented if it is a line in the city budget. That's the only way that we can have anything happen, is that it gets into the budget. And so, and I like this. This is a quote from Noel Cressy from the talk he gave last month at the World Statistics Congress, where he said that it's not enough for us to just come with the knowledge. We have to do more on top of that, because we have to use the knowledge to make decisions. And he claimed, and I very much agree, that actually we statisticians, we can do a lot up here in terms of helping generating the knowledge, but it's also very important for us to be involved here in going from the climate change knowledge to the actual decisions and the adaptation. And so what I am going to tell you today, hopefully convince you, is basically this one thing, that even if the decision maker only wants a single number, and we're just going to give them a number, we still have to use the uncertainty in the way that we generate that number. And it's very important that we take account for all the uncertainties in the processes behind the number, even if we don't tell people where those uncertainties go in and how they came about. And so I'm just going to give you we have an example, which is a sort of a proof of concept of this, in that we cut a lot of corners because we wanted to try to show that you can actually do this with sort of a light touch framework, or I call it a light touch framework. When I go to a climate change adaptation conference and present this, they don't think it's light touch. So it's all sort of in the eye of the beholder. And our particular example is sea level rise and adaptation to sea level rise in the city of Bergen, which is on the west coast of Norway. And this here is a sort of an elevation map of Bergen from Google Maps. And you can see that here we have sort of the city center, which is sort of on the ocean on the west coast. And then around the city center, we have sort of tall mountains on both sides. And here, right on the water, we have a UNESCO World Heritage Site, which is regularly flooded in today's climate. And so, and then here we have what is projected to happen to the sea level, so the mean annual sea level, under RCP 8.5. So the blue line here is the observed sea level anomalies. And then we have those red lines here, which are projections under different climate models. And then we have these dotted lines you can barely see here, which are sort of the point-wise confidence bands, and then the black lines are the joint confidence bands. And so we can see that if something is regularly flooding in today's climate, it's quite likely that it's going to be flooded even further in the future. And therefore, there was a report that came out 10 years ago, where they looked into 3 different adaptation measures that they could do in the city to prevent this. So one was built basically out here, sort of out of this picture, out in the fjord. They were going to build a huge outer barrier. It was going to cost more than 30 billion NOK, which is 3 billion euros. And of course, that would have a large environmental and economic consequences. And then as an alternative, they were thinking they could build inner barriers at 2 places in the city, so one here and another here on the other side, that they would be cheaper because they're smaller, but then of course would have limited benefits because they were protecting smaller parts of the city. And so we're gonna basically look at whether or not these are viable options. And so we have some questions. Basically, are these adaptation options appealing at all if we look at a cost-benefit perspective? And if we should adapt, do we have an optimal time to adapt? Because if we do it too early, we're kind of wasting money because the infrastructure has a certain lifetime. If we do it too late, there might be too high a damage cost before we build. So we want to try to optimize the timing. And then we also want to know what are the effects of the associated uncertainties. And we focus on 3 uncertainty components. So the projected sea level rise is uncertain. The annual yearly damage is uncertain. It very much depends on whether or not a big storm is going to hit Bergen or another part of the West Coast in that year. And then how a change in the damage due to sea level rise, sort of how the sea level rise changes the damage structure is also very uncertain. And there's some code for doing this, and there are 2 papers here in Water Resources Research and Significance. And so here is first, we need a model for getting local sea level projections. And for this, we do sort of 2 regressions. So here we have the red is the observed sea level anomalies in Bergen, and then we have to correct for the fact that the land is rising, so that our actual observed sea level anomalies corrected for the land rise is the black line. And then our first regression is to find a relationship between the local sea level anomalies at Bergen and global sea level anomalies. And then we find another relationship between the global sea level anomalies and temperature projections. And then we can use the temperature projections out of GCMs to sort of backtrack through the 2 regressions to get projections for local sea level anomalies. And then we get this. This is the picture you saw before. And this is the same, just to sort of show you what we actually do. So we generate 10,000 different projections for the local sea level in Bergen. And so here you can see that this white uncertainty band is actually needed because it sort of approximates that approximately 90% of the projections should be completely inside of the black lines. So 10% at some point in time go outside of the bands. And then here in color, I've picked out just 3 different examples. And that is just to show you that we really need a lot more than 3 to actually get a picture of the full uncertainty. So we sort of use, in this case, 10,000 different projections. And then we need to know how the damage cost might change due to sea level rise. And this is quite complicated because we have to estimate sort of the socioeconomic development in Bergen into the future. And here we cut some corners. So there was a paper from Lancaster and co-authors in 2013 where they looked into 126 cities worldwide and applied socioeconomic models to project the effects of change due to 20 and 40 centimeters of sea level rise. And so what we did is we took the results for 15 European cities, and then we sort of said that those results are like an ensemble, and a Bergen is like a random European city, basically. And so, so here we have sort of kind of we start here at 1, and then here's a multiplication factor in the mean annual damage if we see 20 extra centimeters of sea level rise and 40 centimeters. And I believe that might be Glasgow. So, and then of course, because our projections are a lot more than only 40 centimeters, so we somehow had to extrapolate this up to more than 100 centimeters. And interestingly, if you're plotting a function, if you have 2 data points and you want to fit a function through 2 data points, you can take whatever function you want and it's going to fit perfectly. So, so we decided to be conservative here and we just fit linear functions. Yes. And you get, that is sort of, people look at that very skeptical, but we tried doing this with exponential functions just to see what happens. And what happens is that you end up with more damage than there's money in the world. So we had to sort of be conservative in some way here. And then the last thing is we needed some way of simulating damage costs. So what we did is we took data from the Norwegian natural perils pool, which, so every house in Norway has to have a fire insurance, and 4% of your fire insurance goes into the perils pool, which will pay out damages due to natural catastrophes. And so they publish how much they have to pay out due to storm surges on a county level. And we have data there from 1980 to 2015, and we have data from the county where Bergen is. And then we looked at the county that is just south of Bergen, where we have another city, Stavanger, and saw that those data sets were very similar. So we put both of them together to get a better fit to our distribution. And then we fitted a bird distribution to the data, and then basically for our simulation, every year we take an independent sample from this bird distribution as to what is the simulated annual damage in that year. And then we can look at the total costs projected over the 85 years, 2016 to 2100. And the black line here is the median projected damage cost if we do no adaptation. And then we have the 95% confidence band here, and you can see the upper limit is a little over 4 billion NOK. So you can see that from a cost-benefit perspective, the outer barrier that was going to cost 30 billion NOK would not make any sense, aside from the environmental aspects as well. And then we have these blue bars here, where basically we ask every year, okay, what if we build the 2 inner barriers in 2016, 2017, and so on? And then if the cost goes below the black, then it pays off to do the adaptation measure. And now you can choose to be risk averse and focus on the upper bound, or not so risk averse and focus on the median line. And the difference in that is about 20 years. So risk averseness means we want to do adaptation measure at around 2040. And if we focus on the medians, around 2060. And then the next question then is, what are the effects of the different uncertainties? So then we repeated this exercise under the 3 different RCP scenarios, where this blue line, this here is the results I showed you on the previous slide, so no adaptation measure. And then what we did is we took 2 of these uncertainties and fixed them at the median level, and then we only included the 3rd uncertainty in the system. And then you can see that, and then we also looked at having no uncertainty at all, so everything is fixed at the median level. And what we see, which is independent of RCP scenario, is that if we don't account for any uncertainties whatsoever, our total damage cost projection is 9 times lower than if we include the uncertainties. And then what is really pulling up the uncertainties is the uncertainty in the damage. And that is because that is the most sort of highly skewed distribution. It is extremely skewed, whereas the distribution for the projected sea level rise is more or less symmetric. It's more or less a Gaussian distribution. And so it doesn't pull up the final uncertainty to the same extent as the damages. So then, of course, the next question we had was, okay, this seems like, does it really matter to have this uncertainty here in the sea level rise projections? Can't we just skip that part? Because it seems like it's not doing very much. So we looked into then including the damage uncertainty and the effect uncertainty, but not the sea level rise. And we see that if we do that, we actually think we have 10 more years of time than we actually have. So it will delay our decision by 10 years. So it actually does matter to include this uncertainty, and also, of course, all the bounds are much lower than they were before. And then, of course, we cut a lot of corners here. So then the follow-up work is to look into things into a little more detail. So what we did in this example was we just looked at the mean annual sea level. We didn't look at storm surges. We didn't look at extremes at all. And then we did this exercise here, a paper that is currently in submission, where we looked at hourly tide gauge data from Esbjerg, which is here on the west coast of Denmark, which we picked because we have a very long data series at this location. So hourly observations since 1891. And here are the mean annual sea levels at this location, and you can see that the sea level is going up. But it's not only the sea level that is going up. We also see that the amplitude of the tide has gone up as well. Now it's much smaller effect, but we see a little bit of an increase here in the amplitude of the tide. And then we again did this sort of looking into potential sources of uncertainty and non-stationarity. So we have the same way as before to generate projections for mean annual sea level. Then we fit a statistical model to the tide, the changes in the amplitude of the tide as a function of mean annual sea level. And then we use that statistical model to get projections into the future based on the simulations. And then to put a residual model on top, we looked at a stationary model that just uses the empirical residuals from the 20th century. And then we looked at actually fitting this using the GEV model that Jonathan talked about, which is non-stationary in that mean annual sea level is included as a covariate. And here is the result when we look at that. So here is, so we have 2 different years. So we have the extreme distribution. So for the different return periods, we have the extreme so the water level for 10 up to 200 years. If we base this on the climate in the year 2000, and then if we do this based on the projected climate 100 years later. And then we have this solid line here, which is our model. So this, for instance, is the 0.99 quantile of the distribution in 2000, and this is the 0.99 quantile in year 2100. And then we have this dashed line down here, which is the official information from the local authorities. So if you have to do some infrastructure calculations, estimates, you would use this dashed line down here, which is what the authorities give out. And this here on top is when we have a non-stationary residual model using the GeV distribution. And down here is when we have the empirical residuals from the last century. And now, unfortunately, the plots here are on all sorts of scales, so let's just talk through this. So here we see that in the current climate, this 0.99 quantile here is a little over 400, and it is quite similar if you look at the empirical residual model. However, sort of the non-stationarity here in the GeV actually adds about a meter to this estimation of the quantile. So we get another meter of what can actually happen by accounting for these non-stationarities. And then our climate scientist, he looked at this and he said, I can't actually go and present these results. No one's going to believe me. This can't possibly happen because the most extreme value in the data series that we have is 430. So 430 is sort of nicely here inside this, but it is way below that. And then he went and did some more investigation, and it turns out that there is actually an extreme measurement of 6.3 meters, or 630, back from 1634, which is not in the record because they weren't doing hourly measurements at the time. But sometimes it can be very, very important to do a little digging and really look at what historical data is available to sort of support your story, because our time series, as Andrew also talked about, are so short that we're really only seeing a little window into the past. And so, just to conclude, I've heard this, many other people have said this this morning, and I just want to repeat that. I think we have a lot to contribute in climate science and climate-related decision-making. We need stochastic models to realistically downscale to a finer grid, which is needed for decision-making. And also, uncertainty assessments and propagation of uncertainty are very important, even if no one wants to know what the uncertainty is. And then it's very important to communicate, learn how to communicate and how to do the right messaging. And I find I struggle with this a lot, so if people have good ideas on how to do that right, I'd be very happy to hear that. And finally, there's a lot of other uncertainties which I haven't talked about, which we're sort of currently looking into. One of them is that there are bad things happening in Antarctica at the moment, which are not included in these calculations. Another thing that is not included is the uncertainty in the discount rates. So how we do the calculations is that when we look at costs in the future, we basically have to
estimate how much money would I have to put aside today so I can afford something in 50 years from now. And then I have to have assumptions about what interest rates are going to be in the next 50 years. And their government gives some indication of how to do this. But of course, that's very optimistic regarding future inflation. So including uncertainty in the discount rate is another thing that we're working on. And that's it. Thank you very much.
Thank you, Thordis. Does anyone have any questions before we break for lunch?
Just that last point. I mean, the discounting rates, presumably, if you put some uncertainty on those, can have a huge effect on the decision making, particularly over the next 10 to 15 years. So have you got any sense of the sensitivity to that at all yet?
No, that's on my to-do list. But there is in the economic literature, you have some papers where people try to come up with models for discount rates, which include uncertainty. But there's a lot of issues. I mean, we've had some negative inflation, right, in the recent years. And there's a question like, should you allow that, or should you only allow positive discount rates? So there's a lot of questions there that we've yet to answer.
Okay, I'd like to thank all three of our speakers again.